Assalamualaikum warahmatullahi wabarakatuh. Hi guys, we'll meet again. Like before, I'll explain about physical chemistry, and today I'll discuss about phase equilibrium in simple systems, the phase role, such as we'll discuss about the equilibrium conditions, stability in the basis of a pure substance, pressure difference of mu versus temperature curves, and for the last, clapeyron equations. And guys, hope you guys can enjoy my explanations. Okay, first we're talking about equilibrium conditions. For a system in equilibrium, the chemical potentials of each constituent must be the same everywhere in the system. If there are several phases present, the chemical potential of each substance must have the same value in every phase in which that substance appears. For systems of one component, mu equal G dividing the fundamental equations by n, we obtained derivation of mu equal negative molar entropy times derivations of temperature plus molar volume, the derivative of pressure. And then after we know about the equations, we obtained tau mu dividing tau temperature of pressure equal negative molar entropy, and tau mu dividing tau pressure of temperature equal molar volume. Here that we get the equilibrium conditions. Okay, that's about the equilibrium conditions. Okay, for the next is stability of the phase of a pure substance. By the third law of thermodynamics. Okay, for the next, we have a stability of a phase of a pure substance. By the third law of the thermodynamics, the entropy of a substance is always positive. This fact, combined with equations last, show that dou mu divide dou temperature of pressure is always negative. Consequently, of a plot of mu versus temperatures at constant pressure is curved in a negative slope. That is dou. For solid, first for solid, dou mu solid divide dou temperature of pressure can obtain negative molar entropy of solid. And for a liquid, dou mu liquid dividing dou temperature of pressure was obtained negative molar entropy liquid. And for the gas, also same, dou mu gas divide dou temperature of pressure can obtain negative molar volume of gas. At any temperatures, molar entropy of gas is bigger of a molar entropy of a liquid, and molar entropy liquid is bigger than molar entropy solid. The entropy of a solid is small, so that in figure 12.1, this diagram is the mu versus temperature curve for a solid. Curves entropy has a slight negative slope. The mu versus temperature curves for the liquid has a slope which is slightly more negative than that the solid curves L. Here solid, liquid, and gas. The entropy of a gas is very much larger than the solid than that of the liquid, so the slope of curves G here has a large negative value. The curves has been drawn as straight lines. They should be slightly concave downward. However, this refinement does not affect the argument. The thermodynamic conditions for equilibrium between pairs are constant. Pressure are immediately apparent in figure 12.1. Here, solid and liquid coexist in equilibrium when mu solid equal mu liquid. That is, at the intersection point of curves solid and liquid, the corresponding temperature is Tm, the melting point. Similarly, liquid and gas coexist in equilibrium at temperature Tb. The interaction point of curves liquid and gas at which mu liquid equal mu gas. The temperature axis is divided into the three intervals. Below Tm, the solid at the lowest chemical potential between Tm and Tb. The liquid has the lowest chemical potential. Above Tb, the gas has the lowest chemical potential. So, the phase with the lowest value of chemical potentials is the stable phase. If liquid were present in the system at a temperature below Tm, like here, the chemical potential of the liquid would have value mu A, while the solid has the value mu B. Thus, liquid could freeze spontaneously at this temperature, since freezing will decrease the Gibbs energy. At a temperature above Tm, the situation is reversed. The mu of a solid is greater than that of the liquid, and the solid melts spontaneously to decrease the Gibbs energy of the systems. At Tm, the chemical potential of the solid and liquid are equal, so neither phase is preferred. They coexist in equilibrium. This situation is much the same near Tb. Just below Tb, liquid is stable, while just above Tb, the gas in the stable phase. The diagram illustrates here familiar sequence of a phase observed if a solid is heated under constant pressure at low temperature and the systems is completely solid at the desired temperature Tm, the liquid forms. The liquid is stable until it vaporizes at temperature Tb. This sequence of a phase is a consequence of a sequence of entropy values, and so is an immediate consequence of the fact that heat is absorbed in the transformation from solid to liquid and from liquid to gas. So that's about stability of phase of a pure substance. So next we're talking about pressure difference of mu versus temperature curves. At this point, it is natural to ask what happens to the curves if pressure is changed. This question is answered using equations of here. Derivative of mu equal molar volume derivative pressure here. So if the pressure is decreased, derivations of pressure is negative, molar volume is negative, hence derivations of mu is negative, and the chemical potential decrease in proportions to the volume of a phase. Since the molar volumes of the liquid and solid are very small, the value of mu is decreased only slightly. For the solid, from A to axons, for the liquid, from B to B axons, and volume of a gas is roughly times larger than that of a solid or liquid, like here. So, the mu of a gas decreased greatly from C to C axons. The curves at the lower pressure are shown as dashed line parallel to the original lines in here, figure 12 point times B. That figure shows that both equilibrium temperatures have shifts. The shift in the melting point is small, while the shift in the boiling point is relatively large. The melting point shift has been exaggerated for emphasis. It's actually very small. The decrease in boiling point shift has been the decrease in boiling point of a liquid with decrease in pressure is neatly illustrated. At the lower pressure, the range of stability of a liquid is noticeably decreased. If the pressure is reduced to the sufficiently low value, the boiling point of the liquid may even fall below the melting point of a solid, like figure 12.4 here. Then, there is no temperature at which the liquid is stable, the solid sublimes, at the temperature of Ts here. The solid and vapor coexist in the equilibrium. The temperature Ts is the sublimation temperature of a solid, and it is very dependent on the pressure. Clearly, there is some pressure at which the three curves intersect at the same temperature. This temperature and pressure define the triple point or three-phase coexist in equilibrium at the triple point. Whether or not particularly material will sublime under reduced pressure rather than melt depends entirely on the individual properties of the substance. Water, for example, sublimes at pressure below 611 Pascal. The higher the melting point and the smaller the difference between the melting point and boiling point at 1 atmosphere pressure, the higher will be the pressure below which sublimation is observed. The pressure, it means in atmosphere, below which sublimation is observed can be estimated for substance obeying truth rule by the formula. learned pressure equal negative 10.8 times TB mean TM divide TM. So that was about pressure depends of mu versus temperature curves. And for the clapeyron equations, I think it's simple. Honestly, that was a long way to get these equations, but I think this is the last equations that we must know. And these equations, the clapeyron's equation is fundamental to any discussions of the equilibrium between the phase of a pure substance. Note that the left-hand side is an ordinary derivative and not a partial derivative. And the figure of a 12.3b, like before, here, right, show that the equilibrium temperature depends on the pressure, since the intersection point depend on pressure. The clapeyron equations express the quantitative depends of the equilibrium temperature on pressure, or variation in the equilibrium pressure with temperature. Here of the quantitative depends of the equilibrium temperature on pressure, and here the variation in the equilibrium pressure with temperature. And using these equations, clapeyron equations, we can plot the equilibrium pressure versus temperature schematically for any phase transformation. So that was about the clapeyron equation. That's so simple, right? So just for this equation and you get the clapeyron equations. Okay guys, thanks for watching. Don't forget to like, comment, and subscribe our YouTube channels. And also hope you guys can stay healthy in our pandemic global condition. Stay healthy and see you. Assalamualaikum warahmatullahi wabarakatuh.